No sleeping during the
I know.
Question there. Since you have a lot of things to say, and so pretty much have one page to say it all,
Mhm.
and so you don't like we have like just a single right,
Papa.
so we have like a page of
Leaving something out.
That's fine.
oh, and I got picture in.
Did you? Okay, good. Well, that's good. All right. Let's get organized
Trying to
here.
send it to 6 was like the hardest thing in the world. We did it around. It was like close. Why they consider one of your doors? Professor, were we supposed to, for the project, were we supposed to center our output at 0.6? Quiescence?
Not. I think you could do with the offset voltage if you want, right? Or I don't think it has to be there, right? That wasn't a spec, was it?
I wasn't sure. For project 1, Sir Rob told me it was. What do you recommend?
No hidden specs. Right, right.
Oh, man.
Just makes it easier, I think. If you, I think if you,
They trying to get us like
did you? Oh, I see. Oh, got extra work on that. Lost the gig. Okay, let's start. We can go. Yeah.
You have like project one.
Do you have project one? Yeah. Why not break? I got a few bunch of things with me here, and I'll hand them back at break. Okay. Yeah. I got some midterms and projects. Okay. Um, so how did the project go? So much fun. Oh, good. All right, so uh, the so I think what's going to happen next. I think you're learning a lot. I mean, I'm getting really good questions from you guys. So I think you're really. I mean, it may be a little painful, but I mean, I think you can see that there. Someone asked just in office hours just now a little bit. Jays, when I start these design projects, I just don't know where to begin. I just don't know what to try. And he said, well, geez, I get some really good ideas by talking to other people. And okay, so first, that's just fine. I mean, talking to other people, looking what other people did. I mean, looking through the book. I mean, that's kind of why there's conferences and stuff like that, because people you can look and see some other people what they did, and all of a sudden, you may not need it right away, but you can sort of file it away, in some time or other when you might come across something that you can use some new ideas. Bang, they become available. Right now, you don't have a whole lot of history, right? And so don't be discouraged that when you sit down, a whole bunch of new ideas just don't pop to your head. I mean, generally what you do is I think analog design is like a whole, like you got a little library of things. And as you get more experience, you get a bigger library. And when you come to a new problem, you can use one of those things you know before. And occasionally then you have to come up with something new because nothing you knew actually works. And then you got to try something else. That's kind of your mode all the time now, since everything is kind of new. So you're kind of it's a little more difficult, I think. But doing projects like this is exactly the way you'll learn. Because once you do this, now you'll know there'll be a set of little design things that you know about now, what you've done these last two projects. It'll just be really useful to you anytime you do something in the future. Like the third project, which is not coming too far off, right? So I'd say the third project, what we'll do, it will be, I think we'll keep the same output swing spec, same load, but it'll have feedback around it, okay, this time. And I think what you'll find is if you start from the project you did this time where you really maximize speed, you'll find out that it's going to be really difficult to make it stable, right? So I think that'll be interesting to you. All right, and then that means you get to go back to your first project that was probably really stable because that was so slow, right? Right. So you're going to need something halfway between your first project and this project that actually works. So that's kind of what's coming for you. And I think that'll be really interesting for you because it'll be everything together. Yeah,
Can you express me
Mike,
again
use the
why
use them.
Can you explain why we have more poles that is shown on the test bench?
More poles and
Pole.
okay. Okay, so first, when you get this pole zero thing, I've mentioned a couple times to you, the dot PZ, when SPICE does the calculation, it does a lot of poles and zeros that are right on top of each other, right? It's okay. So, and there's one that, and if these two numbers are about the same, then a pole and zero has no effect on the real transfer function, and that comes from the finite word length. In fact, I was just, as we were leaving the other day from class, the dean of engineering, Richard Newton, okay, right, is what he did for his PhD project was actually put that pole zero solver into SPICE. That was kind of what his PhD project was a long time ago, when the first versions of SPICE. And I wouldn't doubt that the version that you're using now uses that same code, because what everybody did was took the version of SPICE that Berkeley had, and they'd add a bunch of stuff to it, make it better in some ways, and then sell it, right? And so there's no, I wouldn't doubt that what Richard's code's in there, right? You're using some. Anyway, but just because it's finite, you're solving a big polynomial, and you're going to get just inaccuracy of just finite arithmetic. Floating double precision floating point still gives you errors, and so that's why you see a lot of them. Okay, there's a lot of extra zeros and poles. These two things just cancel each other out. They're nothing to do with the physics of the circuit. It's just the the numerical accuracy of the solver, right? Now there's other poles and zeros that are showing up. Like I told you, I kind of gave you an example. If you have two paths to another node, like the differential pair with current source loads, you have two paths, and the two paths have different transfer functions. That turns into a pole zero pair, okay? It's not like another real pole's happening. In the pole zero pair, it will cancel out eventually, right? But that also gives rise to some extra poles and zeros that you may not be aware of, right?
Another question. Like the transfer function diagram, right? Why? Because on mine, is there a little
bump?
Tiny one, and
yeah, a lot of you got this little bump thing here. What that's probably coming from, and you kind of understand it now a little bit. You probably used a source follower in their circuit, did you? Yes, you did. Yeah, right. So okay, so what happens with a source follower is that looking into this output, okay, it's actually a feedback circuit, as we talked about last lecture.
Can we switch the camera?
You switch the camera. Yeah. He's got midterms too, looks like. All right. So the looking into this this is a feedback circuit, like we talked about last time, right? This is a series shunt feedback network. Okay. Once you have feedback, poles and zeros can begin to move off the axis. If you just have a straight RC network, okay, then the poles are all on the axis, and you'll never get a bump like this. As soon as you get feedback, and this is a feedback network, the poles actually will begin to move off the axis. Okay? They become complex. When you get something like this, in fact, what they can do is, depending on what the circuit configuration and how much gain you have, these poles can actually begin to move towards the right half plane. I'm sort of doing a plot here of pole movement as a function of gain, let's say. Okay? As this is the j omega axis, the sigma. As the poles move towards the right half plane, if they get over the right half plane, the thing's unstable. As they move towards the right half plane, it's moving towards instability, and that's what's beginning to happen here. These poles are moving towards the right half plane, and you're seeing a little bump here because you're beginning to get amplification, at this frequency. You can tell where the poles are. Where that bump is happening is a set of poles that are getting near the right half plane. That's causing this little instability issue. Yeah.
So the height of that thumb, it depends on how much gain do you have, right? If the gain is too much, then you got a really huge Otherwise, because if it's soft follower, then it's just gonna the gain is approximately 1.
Well, remember, the closed loop gain is 1. Closed loop gain is 1. But what was the open loop gain of that source follower? Remember my last lecture? Yeah, right. Something or other, yeah, right. It's GM times RS, actually. That's the open loop gain, if you look back in those notes. Okay, it's GM of this transistor times RS in parallel with R0. That's actually the loop gain of this circuit, and that's what's really important. It's the loop gain I'm talking about when I'm moving these poles around. Don't panic on this. That's what I'm going to be talking about next week. Okay, right? So we'll go into this in gory detail, but you're beginning to see this effect. Okay, and as you make a circuit more and more unstable, with too much gain, what will happen is things will peak even more and more. And finally, it goes to infinity, and that's when it oscillates. Okay. So you're beginning to see some of the effects of, it happens. It's because source followers are actually, in actual fact, if you calculate the output impedance here, looking into here, it looks inductive. Okay? And if you have some capacitance here, because that looks inductive, but if you just go in here and calculate it's in the book, I didn't do it, but if you go in there and take the output impedance value, replace include the effects of some of these capacitors, and calculate what the output impedance is, you'll see it's inductive. And so that can resonate with other capacitors. That's basically what's happening. You've got an inductive capacitor tank circuit that's beginning to oscillate in effect, right? It's another way to look at it. Right? Okay. Got it?
Just a quick question. I forgot, is this when the pole is under left half plane?
Stable.
This is very stable, right? And then we start moving.
Right, right. Yeah, poles on the right half plane cause an infinite response. I mean, a small amount of noise will take it up and it'll just keep it. Poles on the left half plane are all stable. Any response will decay over time. So next week we will start the stability stuff, and I'll do a lot more of that. But you're beginning to see the effects of it already. Okay, let me just summarize what we've been doing. There's 4 different kinds of feedback. We've talked about, I think, series, shunt. We talked about shunt-shunt. I'm going to do shunt-shunt again right now, okay, just because that's a real clean example. And then we'll look at some series feedback, and we can look at shunt series feedback, okay? Let's show what these are. So series, I'm going to do a shunt-shunt. So let me just do this. I'm going to do it slowly. There's actually a little tricky business in this shunt series thing, or shunt-shunt, that I want to go through. So let's do this real carefully. We'll do it. It's a simple example, and we'll just work it all the way through. Okay? So here's the problem. There's the pins out of ink. Okay, try again. Nope, don't like that one. Let's find this one. Okay, here we go. Let's define the problem as this. Okay, let me get a pad of paper here. Vn. Okay. Let me just make this I'll make it RD. And we have, okay. So let's call this I think in my notes I called this RG or something like that, right? Or I don't know why I did that. Oh, R gate, I guess. RF, okay, and this is RD, okay? And let's say that RD is much, much less than R naught, so I don't worry about the R naught of this transistor. Okay? Trivial included, to be in parallel with RD. So what I want to know is this. I want to know what the input resistance in here to this point is. Okay. I want to know what the output resistance is. And I want to know what the gain is. V out over V in. Okay, so the first thing you get a problem like this, what kind of feedback is it? Okay, you got to look at it. The best test to look at is if you have your feedback. You look at this circuit, you sort of see an amplifier here, this common source stage, right? And you see this little RF thing. Well, that's something and it's kind of coupling from the output back to the input. That looks like feedback. Okay, now we got to figure what kind it is. So we kind of take our basic amplifier, which is probably this little common source stage, and the feedback network is coupled right to V out. It's connected to the V out point. That is a really good clue that you have shunt sensing. Okay, that's the easy thing to look at. As soon as you see that, you can sort of detect that you've got shunt sensing. Okay, so this is dash shunt. Okay. Now, how does it connect back into the input? Shunt sensing means you're sensing a voltage. Coupling back in the input, you see this input voltage here, and you think, well, geez, maybe this is series feedback. Okay, there was feeding back a voltage that's in series with the input. Because you see a voltage here, right? Because series feedback is a voltage kind of type of feedback. But we look here. Are we differencing with that input voltage? Do we somewhere establish in order to have series feedback, we have to have V error equal to V in minus V feedback. Okay, here's V in. Where is V feedback and V error? Okay, is it right here? Do we call that V feedback at this point? If we call that V feedback, then that's directly onto our gate. Well, that's not a V error there, right? And where is V in minus V feedback? Well, V in minus V feedback kind of across this resistor. Well, that's not doing any differencing there, right? There's no differencing going on. I'm not establishing a new voltage that's being applied to an amplifier, right? I mean, I'd have to have V in minus V feedback somehow applied to this gate. That's not happening here. So this is not series feedback, okay? This is shunt feedback. So even though I got a voltage here, you can't look and just see what the voltage is, and you can't even see, and I'll give you some examples pretty soon. Even if you want to take a V out, an output voltage, that doesn't necessarily mean that you're doing shunt sensing either. I could be sensing a current. In this circuit, I'm not. And I'll show you what those circuits look like in a second. Okay, so this, I claim, is shunt feedback. If it's shunt feedback, that means I got to turn this into a current input with a voltage output network. Okay, so shunt. So I got to do the Norton equivalent of this input, and that's V in over R in. V in over RG. I'm sorry. All right. V in over RG. And the Norton equivalent will have an RG in parallel. Okay. And then I go into my amplifier. So this is exactly the same circuit. Or it will be. Here's RF, here's V out. So now I have a current input instead of a voltage input, so I'll call this I in. Now, can we see a differencing going on here of currents? And I claim I can. I will claim that this is IF, or if I define it that way, I feedback. Okay. This is I in coming into here. Okay. And here's and this is I air going into here. Okay. So I have a little extra resistor stuff going on here, but I have an I in, an I air, and an I feedback. Okay. I need to. This RG is a little troublesome here. I should have placed it either as part of the feedback network or part of the basic amplifier. I didn't do either here. So let me do that. Let me connect this over to here. Okay. And I'll call this I air, right? And this is I feedback. Okay. I just got to be consistent. I got to have a differencing node. I can put this RG. I could have stuck it up here as part of the feedback network, or I can leave it down here where I make it part of the basic amplifier. Doesn't really matter. Okay, but I got to have a differencing node like this somewhere. Okay, so this is not what we have. What we really have is I air equals I in minus I feedback. Okay, so now let's just look at our feedback network by itself. So here's V out right here. Here's RF. Okay. And this is, I'm defining my feedback current in this direction this way, so I can see right here. Okay. And F, the feedback factor, is going to be equal to I feedback over V out, right? The signal's going in this direction. Okay, this is the input to the feedback network. This equals V in of the feedback network, right? Equals V out of the base of the amplifier. Okay. Well, what do we do? If I have a current output, in order to figure out what the current is, what do I have to do? I have to short this to figure out how much current I have flowing into this output. And you can see by shorting that, I can write the equation that I feedback is equal to V minus V out over RF. Or F is equal to V out, I feedback over V out, which equals minus 1 over RF. So the feedback factor for this guy is minus 1 over RF. See, I do that. Current output, I need to short it. Shunt, I need to short it. A bunch of ways to think about it. Okay? Now, we need to go back and figure out the basic amplifier with loading. Okay? So here we go. So let me just redraw that for you so I don't make this so messy like I've been doing. Here's RD. Here's this. Here's RF. Here is RG. And here's my IN. Right? Okay, so this is our amplifier. Now if I got to find the gain, what I'm trying to do is, remember how I'm doing this. So this is the feedback thing that we're working with here, right? This is a V out, and these are currents here. This is an I feedback, and this is an I in. So I'm trying to find now this amplifier, which includes the loading effects of this basic amplifier on this, as part of the degradation of the gain of this amplifier. This thing has a finite input resistance, and it'll have a finite output resistance and a current source, right? Well, I guess it's a parallel, right? So I got to include this resistor loading down this output. I have to include this resistor here as somehow maybe differencing some of this input current. All the current's not going into the basic amplifier. Some of it's going into the feedback network. Okay? So what I need to do now is so here my feedback network, remember, looked like this. So this is V into the feedback network, and this is I out of the feedback network, right? And I guess, well, I drew it in this direction, I guess, right? Okay, but it's minus, so tell it. Okay, now, what is the loading effects? Okay, so looking from the output, so let's draw our amplifier. Here's our RD. And I want to hang off this output here, the output of this, including the loading effects of this RF. And what is it? So looking from this side, looking into here, basically what I'm trying to do, that's why, I'll just stay up here. Looking into this, what do I assume about this side of the feedback network? Grounded, right? it's a current input. This is a current point here, so I assume this is a short circuit, right? What? Right. Right. Okay. Right. Okay. So here we go. Yes. Yeah. Okay. Right. Okay. So I followed myself a second. So that means it's an RF to ground. Looking there. Okay. Looking this direction into this feedback network, the loading effects on the input side, what do I see on this side? What do I do with the input to the feedback? In other words, what do I do with this side here? Short or open? Short, right? Because the voltage on this side, that's a short. It's shunt, it's a short. Okay, so shorted. So in other words, looking this way, I see an RF as well. Okay. And I have an RG going down, so I'll just make that RF in parallel with RG. So this is our new basic amplifier. So this is the new basic amplifier with loading. Okay. It's a trans resistance amplifier, right? This is IN. Right? Current in, voltage out. So I need to calculate an A sub R, a what I'm going to do now is get a new basic amplifier. It's going to have a new input resistance, and it's going to have an output voltage, and here's an R out. Let's call it RO. This is an RI, let's say, and this is an AR times IN. All right? This has units of resistance. This AR thing does, right? Current in to voltage out. Okay. What is AR equal to? AR is going to be equal to AR equals V out over IN. And what is that? Well, if we take IN times, so the voltage at this point right here is going to be IN, so this is kind of a VN, equals IN times RF in parallel with RG. So that gets the voltage here. That times G sub M gives me the current here. That G sub M, so G sub M times this voltage, that'll be I out, let's call it. So I out equals G sub M times V in, okay? And V out is going to be equal to I0 times RD in parallel with RF, all right? So I got GM times RF in parallel with RG times RD in parallel with RF. So we'll do that. So A sub R is going to be equal to GM times VN, which is RF in parallel with RG. And that's we got to calculate V out, which is that's I0 times RD in parallel with RF. Okay? So this has units of resistance, right? GM times R is unitless, times R is, so that gives us units of resistance. And this is with loading, right? Get the idea? See, without loading, this simply would have been GM times RD, right? If we didn't include any effects of loading. So this AR includes the effect of loading. I've been calling that prime, so let me call that prime. That's the loading. Without loading, this would simply have been, we wouldn't have had the two RFs here, right? We'd end up with GM times RG, actually, times RD. That would have been without loading. So this is without loading. Without loading of the feedback, and this is with loading. Okay? Now, what about what's t, or t prime? That's what the loop gain with loading. It's going to be AR prime times F. And what was F? We calculated F a long time ago. F was equal to minus 1 over RF, okay? And the polarities of these things, once you check it's negative feedback, I just would stop worrying about the polarities. You got to check this negative feedback at one time, you know, and you can sort of go around the loop. This, you can sort of say, okay, starting, let's see here, starting at this point right here, this is a voltage at this point that drives a current into that node, okay, which increases the voltage on that node. Increasing the voltage on that node then decreases the voltage here, so that means it's negative feedback, right? So it's positive from this direction and negative there, so you got negative feedback. So once you did that, stop worrying about the signs. So AR times F, and this is going to be simply GM times RF in parallel with RG times RD in parallel with RF. And F is 1 over RF, so this is all over RF. Okay? Now, okay, so what's our gain? So what's the gain of this circuit? Okay, it's going to be V out over IN. Remember I'm calculating V out over IN. I'm not calculating V out over VN. That's what I originally asked for, but I converted into this current problem, right? So V out over IN, that's my answer is going to give me, is 1 over F times T over 1 plus T. Here's the minus sign. You can leave that in if you want. Minus, and 1 over F is 1 over RF, so this is minus RF times this T prime over 1 plus T prime. If this is much greater than 1, and we have to check to make sure this is true, you can put some numbers into here, but you got GM times this RF in parallel with RG factor. That gives you a bunch of, or GM times RD in parallel with RF is kind of the gain of the circuit. And there's RF in parallel with RG over RF. If this thing works out to be greater than 1, okay, much greater than 1, then you can remove this, and the answer to this, and it very likely is, unless you've fouled things, you want this to generally be much greater than 1. If this thing's not much greater than 1, then you don't really have a, you know, you're not using feedback to any usefulness. Okay, so it's going to be approximately equal to minus RF for T prime much greater than 1. Okay, that's V out over IN. That's not what we want. What we want is V out over VN. All right. So if V out, let me skip up here. So V out over IN, and IN we said, we can look over here, IN is equal to VN over RG. So I replace this by VN over RG, and that ends up by RG comes up here, then it goes on the other side, so I end up with minus RF over RG. Okay? So here's our gain. A little bit of trickiness in these shunt feedback things. If you start with a voltage, you got to end up converting things back to a voltage again in the end. Okay, what's the input resistance? Now here we're tricked again. What we're going to calculate for input resistance is looking into here, right? This is the input resistance, and let me call this Rn prime. This is the input resistance we're going to see here. What I really wanted was the input resistance from this voltage source. But that's not what I'm calculating here. So I'm going to get this value, and then I'll figure out what this is. Okay? So looking into here, this is Rn prime, and what's that answer? Rn prime is going to be equal to the Rn of my basic amplifier, which is RF in parallel with RG, RF in parallel with RG, divided by 1 plus T prime. And if T prime is much, much greater, oops, is that right? Yeah, that's right. Okay, right. Shunt shorter, right? Shunt smaller, right? So T prime we've calculated before. That's this guy right here. And I got to plug that into here, right? And let's say T prime is much, much greater than 1, so I'll get rid of that. So I end up with RF in parallel with RG all over GM times RF in parallel with RG times RD in parallel with RF times over RF, so an RF comes up in the numerator here. Okay? Now, notice what happens here. RF and parallel RG and RF and parallel RG cancel out. And the denominator has GM times RD in parallel with RF. So what's that? This is basically the gain, the loaded gain of this amplifier. You know, GM times RD in parallel with RF. It's kind of the gain of this basic amplifier. Let me call that AV. Let AV be defined as GM times RD in parallel with RF. It's the basic amplifier with loading. So the Rn prime is equal to Rf over this AV prime, let's call it that. Okay? Notice something here. This is pretty tricky. Remember, we always worried about that Rg. Notice that this input resistance, looking into here, this is really weird. There's an Rg here that we have all this worry about, right? Where do we include it? Notice that the answer here, not even these two things cancel out, has no Rg in it. So the input resistance looking into here is not a function of Rg. Now, you're so sleepy you don't understand this right now, but but when you wake up, this should be really surprising to you. Okay, so. But in effect, what this is, I told you all this problem of deciding where Rg goes. It doesn't matter, right? The answer ends up independent of it, right? So that's pretty weird. I mean, okay, but the input resistance of looking into here is simply the feedback resistance divided by the gain of this circuit. Okay? It's small, right? So the more gain you got here, it's going to get smaller and smaller, right? Yeah.
But you said like the gain of a circuit is equal to negative RF divided by RG. So if you put that in, so should it be just equal to negative RG?
This is the basic amplifier gain here, right? This little AV here is the open loop gain. Okay? AV is the open loop gain. And it's equal to this, GM times R out, basically. Okay? And the loop gain, the closed loop gain is this 1 over F T prime over 1 plus T prime, right? And that's minus R. So this is the closed loop gain. Okay. And what is R out? Okay. So let's do the last thing here. R out. Oh, let me finish up here. This is not what I wanted. Okay. Here's the rest of this. It's actually pretty tough material for today. This is the Rn looking into here. But what I really wanted was the Rn looking into here. Okay? So how can I figure this? How can I get from here to here? Okay, so here's what I can do. This is just this is nothing sophisticated. It's just trying to. What I really need is what is the resistance looking into there, right? That's the real value that I need. Okay. Let me I'll say this in words and see if you buy this. Okay. Looking into here, okay, so now, but the problem I calculated was this one right here, right? It's not a function of Rg, right? So let me just give you a little thought experiment for a second. So let's just forget about Rg because the answer it's not a function of that. I could make Rg infinity, okay, and I get the same answer. So looking into here, the answer that I got was RF divided by AV. A really small number, because the AV is going to be very large generally. So looking into here, this number is very small. So over here, so in other words, looking into this point right here, this is basically RF divided by AV. This number is really small. It's in series with RG. So Rn is going to be equal to Rg plus Rf divided by AV. But AV is large generally, so this is simply going to be just Rg. So looking into this kind of circuit, you'll just see Rg. This feedback just makes this node right here be a very small impedance value. Okay. That's probably good as a way to talk about this as you want. Okay? R out. R out. What's the R out? R out is looking into here. No funny business this time. Our basic amplifier with loading was an RD in parallel with RF. It's going to be a shunt. It's a voltage output, should be smaller, so it's going to be divided by 1 plus T prime again. RD in parallel with RF. Over in T prime we had somewhere right here. Remember, it was GM times RF parallel with RG times RD in parallel with RF over RF, so I bring RF up in the numerator again. The RDs in parallel with RF cancels out this time. So R out is equal to RF over GM times RF in parallel with RG. So this is so it's not such an easy way to analyze this. Right? This does have RG in it, right? So it's kind of weird. The output resistance, notice this has no RD in it. Okay? So the output resistance is independent of RD. The input resistance, looking this way, is independent of RG. That's how it is. What's going on is actually the amplifier loading effect is actually making this work out the way it is. That's what's causing it to do this. Because the loading effects are what are making this cancel out, right? So as the gain goes down, I can sort of say this. I mean, RD reduces the output resistance, right? Because it's in parallel with whatever you see looking into here. So RD reduces the output resistance. But it also reduces the loop gain, right? So since it's reducing the loop gain, which is trying to reduce the output resistance too, that reduction of the loop gain makes the output resistance go up. So RD makes it go down because it's in parallel, but the fact that it decreases the output loop gain makes the output resistance go in the other direction, so the two cancel out.
Question?
Same thing's happening in the input. Yeah.
I'm kind of confused with the polarity right here.
Polarity?
T is equal to AR
1 over F. The loop gain's always negative, right? And so you take it minus that, and so we end up with positive, because you have to have negative feedback, right? And so T will always end up to be negative if you keep track of all the signs. So once you know it's got to be negative feedback, then just worry about the magnitude of it, all right? So, don't like that, huh? You always got to have negative feedback. You got positive feedback, you're sunk. Okay, your circuit doesn't work. Okay, so check to see if you got negative feedback, and I did that, right? So, I mean, going from here to here is positive. I mean, going from here to here is negative, here to here is positive. So, okay, so that's negative feedback. Yeah.
What do you mean, positive, negative?
If I have a current going into this point right here, okay, it's going to be, I will have a positive voltage here, right? I'll have a current in this direction, which will be a current in this direction, which is in the opposite direction that I started off from. So I'm looking at this little loop right here. I'm going around this little loop right here. So I start with a positive current, and I end up with a negative current going the other way. So it's a negative current. So the current here is in this direction, current here is in positive direction. So I'd say that's, if this current had come in the same direction as my input, if a current going in here had a increase this voltage, make this voltage larger, that would make this current go this way, and that would be in the same direction. That would be positive feedback. But current going into here actually makes this voltage go negative, which makes the current in this direction, which subtracts from this current here, so it makes it a negative feedback.
So, so you're saying that when we calculate the input resistance and output resistance, we just take the absolute value of the T?
Yeah. I mean, T is always negative, right? It's negative feedback, right? So you need to take minus T. Okay, always take minus T when you're down here. When I defined T early on, I threw out the minus sign. The way I did it, remember, was I had, the reason I did it, because remember the way I started off, I said this was a differencing network here. So that's where I got rid of the minus side of the T, right? I said here's F, or here's F's this way, right? And here's A. So I had AF is equal to T, but there's another minus sign here that I got rid of.
So when you talk about the current going into the gate, you mean AC current?
Small signal current, right?
Okay. And also you say the input resistance is independent to RG?
Right. Input resistance is independent of, for this case here, not this one here. This one here, it's independent of RG looking this way, and this is independent of RD looking into this way. So feedback does some pretty weird things. I mean, you got to be pretty careful with this stuff, right? The zeroth order thing, though, you got to figure out what are the really key things here. Identifying what kind of feedback. You can sort of see if you missed what kind of feedback you had. If you said this was series shunt, and you used the wrong formula, right? Rn times 1 plus T, you'd be off by T squared, right? You make a pretty big mistake if you don't identify the feedback right. So that's why it's so important to be able to identify what kind of feedback any circuit is. Because once you know that, then everything kind of falls out pretty easily, right? You know that looking here's got to be low impedance, and you can go on from there. Okay?
I forgot that in the beginning, you show how to tell the type of sensing, but I kind of missed that.
Let me do some more examples. Okay, that's tricky to do this. So, okay, so brute force solving that problem. Do you want to take a little break here? Yeah, okay. Let me hand back homework, hand back stuff here. Okay, so take a little break. We'll take a little break, and I'll hand some stuff back. Is Loy Fat Din here? Okay. Here's your project, but I don't have the score. Well, we did figure out the score. Let me keep it more. Okay, so sorry. You almost had it. It was close. Okay. Wind tune here. Jun Niu, NIU. Shiji Lee. Yeah, if you know these people, you can take it to them. That'd be fun, right? Loy Din. Yes, right. Yep. Ann Lam. Joshua Chang. It's not there. Rock Liu, Liu. Nurachman Liu. Bagir Afshar. Yeah. Guanan Zhu, XU. Yeah. And Si Lun Chu Lai, LAI. Yeah, you can come here. That's fine. Okay. If you have projects, I'll take them right now. Okay. Okay, ready? Let's go. I'll make this easier. I won't do so many equations this time. Okay, let's talk a little bit about how you identify what kind of feedback. So let's look at this one right here. This is I claim a series shunt. Well, we shouldn't show you. I'll give you a new one. Let's let me draw one here for you. Okay. Okay, so let me do 2 stages. Let's feed back in, and let's call this, let's have a resistor here, and we'll have a Vin. Okay. Let's start off with feedback from here. I'll do a couple of them here. Let's try this. Okay. What kind of feedback is this? In fact, you can't tell till I tell you where the output is. All right? Now that's a little bit of weirdness. You have to know what the output is. Okay, I want the output here. Okay, now, what kind of feedback is this? Starting from here, going back into here. Any takers?
We have 1 in 4 chance.
What?
We have 1 in 4 chance.
1 in 4 chance. Exactly right. If 4 people can do it, we'll finally get it, I'm sure, right? Okay, well, hopefully we're going to get a little bit better odds now by... Okay, let's take rule 1. If you're directly connected to the output, this is directly connected to the output, what kind of sensing is that? Shunt. So we're directly connected to the output, it's shunt sensing. We're fed back into the input here. Is there some place where we're doing some kind of differencing? Let's call this V feedback as a shot. And here's V in. And we call this, we have to include this as sort of the basic amplifier. And so this is V errors being developed right across here. So sure enough, we've got Vn minus V error because Vn minus V feedback. So this is series shunt feedback. Wide series. Here's Vn, okay? And actually I should define the error voltage. If this is all part of the basic amplifier, this Rn, let's include part of the basic amplifier. There's an error voltage developed between here and here. And here, if we call this V feedback, so all these things are in series. Here's Vn, right? Here's the error voltage, and here's V feedback. So it's a series sensing, series feedback, right? Shunt. Okay, let's do a shunt. That's what we just did, right? So shunt looks like an example of a shunt would be something like this. Well, we can do this. Let's do it here. Let's take this output here. Is this negative feedback? We should check that. Okay. Starting here, okay, I go to here. That's negative to here. I go through here, and back to here is positive, right? So I got 1 negative and 1 positive, so this is negative feedback. Okay. So let's do this one. If I connected this from here right to there, what would happen? Would we have positive or negative feedback? Instead of connecting it down here, let me connect it to here. Let's figure out what kind of feedback it is first, okay? Then we'll check to see if it's negative feedback or not. So now this I'm connecting this right to this input. Do we difference with the input voltage now? So this now is coming in shunt. So if I define this as I feedback, right, and I do my little parallel business, let me call this I in, then this will be I error. So this is shunt feedback. Now, is it positive or negative? We start here, we go to here, this is negative, cross an inverter is negative. I go from here to here, negative again, it's positive, so this voltage goes up, that voltage goes up, that puts a current in this direction, which is the same direction I started. I got troubles. So this is negative, positive feedback. It's not going to work. So where can I connect it? I can't connect it there. But what I could do is do this, right? I could go down to here. So what kind of feedback is this? So it's still shunt feedback, because I didn't change that side. Now, am I directly connected to the output? No. So this is series sensing. Series sensing. This is like this. Like, we had this before? We haven't had this yet, actually. This is output current. So this is like a little bit like we did that input side. V out is equal to I out times RD, right? Or minus that. Okay? But I'm not connected to that voltage. I am actually sensing the current out here because I out equals I out. So series sensing is always usually like that. You're sensing on the other side of a transistor, okay? So sensing it down here, the current's up here, it's the same as the current here. The fact that we're looking at V out doesn't really matter, but because we can do this little V out equals I out times RD. We're not directly connected to that output voltage, so this is series sensing.
So that means if the feedback is directly connected to the output, that's shunt. It's not directly, that's series.
That's pretty much right. That's yes.
Okay.
The only way you can get if the feedback's not connected to that output voltage, you're not sensing it, right? And it's got to be the other one. I think that's probably a way to look at it, right? Look what I can do here. This is what's really kind of weird. Let's take V out from down here. I didn't change anything. All I did was change the name of where I take the output. What kind of sensing is this? Shunt. So this is shunt feedback. So taking the output from up here, it's shunt series feedback. Taking the output from down here, it's shunt feedback.
Can you show the path of the current, show whether the is in positive or negative feedback?
Okay, we'll start here. You got to go start somewhere in the loop. Doesn't matter, and you just got to go all the way back around again. Okay, so let's start here. Okay, so a current going into here causes an increase in voltage here, which causes a decrease in voltage here. A decrease in voltage here, this is a source follower, causes a decrease in voltage here. A decrease in voltage here makes a current flow in this direction. Current flow in that direction is the opposite direction that we started with. So, negative feedback.
And also for the shunt, like, not sure if that's called input. Like right now it's shunt, right?
Right.
So if series shunt, then we have that
Be connected down here.
in series with the VR.
VR, right,
But
exactly.
right now it's in series, but shunt means parallel with the UR.
Yes, exactly right.
How can you see that? I don't see that.
Because this is right there, right? Now, where is there a V error anywhere that's being developed? That's being driven, that drives the basic amplifier? Drives an amplifier? Where is a V error being created? You see that? Can you find one? See, if I, attaching to this point, if I call this V feedback, that means V feedback is connected right to that input of this amplifier. There's no differencing. All right? So let me redraw it. So in other words, if it if I come in down here, if V feedback comes down here, and I got a V in here, then I get a V error, right? If I come in like this, let's say I have a resistor here. So that's V feedback on this end, and that nicely differences with this input, right? And I get a V error voltage applied, which goes right across this VGS, okay? If I come in like this, if I call this V feedback, I'm feeding back a voltage. Is that differencing somehow? The V feedback is getting applied to no V, not V in minus V feedback. So I say this has got to be an I feedback, and I got an I in coming in, and I got an I error. Okay? All right? So let's do this series. Here's another one. Okay, so we come in, here's the input voltage. It's coming off, here's a basic amplifier with a load resistor here, right? With a here's something going on down here. You can sort of find the basic amplifier. Here's one gain stage, here's another gain stage, and here's another gain stage. So you can sort of see what's going on here. So there's 3 gain stages. We take the output off here, and I said here's V out. So this is what kind of sensing? Shunt, because I'm connected right to the output. And this is fed back in series with the input because I'm developing an error voltage right across this gate to source voltage. Okay? So this is series shunt. This is what it says on top there. Right? Okay. So here's one I'm not going to. What's this one? There you go. Okay, what kind of feedback is this? So what is it? It's good old degeneration, right? Source degeneration. And I claimed a long time ago that this was a feedback network, and it is, okay? So what kind of feedback is it?
Before you figured it out, since at the audio picture, in the audio circuits, you have the RF, right? The path of RF.
Mm-hmm.
So we can figure out which.
Yeah.
Now,
Always look for the RF, and you know exactly where the feedback is. That's good. That's a good strategy. Yeah, right.
RF,
Yeah, there's no RF here, so you got a more difficult problem this time, right? Now, sometimes people don't put RF in the circuit for you. That's where you have to. So what kind of feedback is this? Series? Series? You should be able to tell from this. Any other guesses, or not guesses? Any other knowledgeable analyses of this circuit? Okay. Are you? Let's check what kind of sensing. Are we connected right to? Where do we see a basic amplifier here? Yeah, probably this common source thing right here, right? So let's call this the feedback network. See how that works, okay? If we call this the feedback network, is it connected to the output? No. So that's series type sensing. Is it differenced from the input? If I call this V feedback, this is V in, I got a nice little V error voltage generated right across this input to this common source stage. So sure enough, this is series feedback. Series feedback. What do we know about the output resistance of series feedback? Does it go up? Does it get larger or get smaller? Larger. Series is larger, right? Shunt's smaller, right? Right? Series is larger. And what do we know this circuit does? It makes the resistance, output resistance, larger. And remember what the factor that it's, what is it? What that factor that it's larger by? It's 1 plus GM times RS, right? Times the R out. And this was the factor it got larger by, right? Doesn't this look like 1 plus T, right? So there's a good chance that with this little term right here is actually the loop gain of this circuit. Is it? Well, we can figure that out, right? We'll do that now. Okay. So what we have to do is, it's tricky about these things is these are almost simpler, right? Because you don't have to break up the transistor itself, get to the small signal model. You can sort of work at the sort of the block level, right? When you work with these things, you sort of got to get down at the, you know, the lower transistor level, right? So we have an input, okay? We have, in fact, I may follow up if I don't. Do I have it here? I don't have it. Okay, so I guess I get to. Well, I should be able to figure it out. Okay, so comes in. There's a GM times. This is input here. Here's our feedback. Feedback's coming on the into here, right? This is series sensing. So we have, let me put this as RD. And this goes into my RS, which goes to ground. So here's VN. Okay. So, all right, so redraw this. Had to get it right first. Okay, so here's VN. Here's our feedback network, RS. Here's our output, GM times, let's call this V error, right, times V error. Here's RD, and this all goes to ground. So this is I out. Okay, so I get from here to here. So here's RD to ground. All right. Here's RS to ground through the current source of this transistor. There's an R0, of course, across here as well. I should put that in, I guess. There's an R0 across there. Right.
Question.
Yeah.
So right now the feedback is between the RS that connected to the input, right? Like the ground connected to the input ground. But you still have that RD connected to the input. They have to
RB?
RD.
RB. What RB?
You take the small signal model.
RD.
Yeah.
Yeah, RD's connected to the output, right?
Right. So that means you also connect the output directly to the, like, there's a feedback directly to the output.
There's no feedback there. See, that's the difference, right? So this is actually sensing a current down here, right? Because there's an I out, and I'm sensing it down here. So I'm sensing the output current down here. So I'm not really sensing that voltage. I happen to take V out. That's the interesting parameter to me, right? And I'll calculate I out over V in, because that's what I'm going to get. That's going to be the 1 over F over T over 1 plus T thing that I'll get, right? But what I really want is not I out. I want V out, right? But it's pretty easy to figure that out. V out equals I out. You know, if I define I out in this direction, it's going to be minus I out times RD. So I'll have to go through, get I out over V in, and then multiply that answer times RD. And that will give me V out. So looking at what, so, okay, so you got to look at what the topology of what's happening. What are you actually sensing? Are you really sensing V out? I mean, are you really, no, you're not. You're really sensing the current in that output stage there. Okay? All right, so here, yeah.
Shouldn't it be like RD parallel with RO? But in the small signal looks like.
Here's an RO.
Yeah.
I stuck it in afterwards. It's in parallel with current source, right? Right. I just took this. Here's RD. Oh, why is it not in parallel? That's a little. Because we're sensing the current now, right? We're sensing the current. We're not sensing the voltage. So I out's what I'm interested in. V out happens to be here, right? But that's not what I'm sensing. I'm really sensing I out. And that's in series with RD. Okay, so now we got to do is we got to make a new basic amplifier with loading. Okay, so how do we do that? What do we do on this side? So looking at, so what is our feedback network? Let's figure out feedback factor. So it looks like this. Here's RS. We're driving it from an I out, right? And this is V feedback. So what is F? F is equal to V feedback over I out, which is equal to what? I out times RS equals V feedback, right? So V feedback over I out is simply equal to RS. So this circuit has a feedback factor of RS. Okay? And you can sort of see now that let's say we had no loading, okay? Let's say R0 was very, very large, okay? What would I out be equal to? If R0 was very, very large, I out would be equal to GM times V air, all right? So the A sub G, this is a transconductance amplifier, right? Voltage in to current out. So if R0, AG would be equal to G sub M. Now we got this R0 here, which provides it's a little current divider between RD and RS, and so in actual fact it's going to be GM with this current divider, which will be simply equal to R0 over R0 plus RD plus RS. It's a current divider, right? Some of the current's going to be lost through R0, and RD and RS are in series with each other. So it's a current divider between R0 and RD and RS, right? You could take RD and put it down here in series with RS, and it's just a straight old current divider. So, okay. So this is so AG is our gain. Here is F. So T prime, this is AG, is equal to GM times R0 over R0 plus RD plus RS times RS. Okay? What's the output resistance looking into here? The output resistance looking into here, this is of the basic amplifier, okay? Looking into here, this is open circuit on this side, right? So I see RS. Looking into here, I see RS, right? Looking this side. Looking this side, I see infinity, so it doesn't matter. So looking into here, this is the basic amplifier with loading, is going to be simply, this goes to 0 because I set the independent source to 0, so it's going to be RD plus R0 plus RS. So R0, RO prime, the output resistance of the basic amplifier is simply R0 plus RD plus RS. See that? I'm doing the two-port equivalent of this thing is what? It looks like I did skip me 2 steps there for you. Here's VN. It's going to look like current source of GM times R0 over R0 plus RD plus RS in series with R0 plus RD plus RS. This is I out. So this is the basic amplifier. That's right. Right? This is the basic VN R0 plus RD with this thing right here. So that's the basic amplifier. So the output resistance is this. So R out is equal to R0 plus RD plus RS times 1 plus T prime. 1 plus T prime is R0 plus RD plus RS. Let's say T prime is much greater than 1. And T prime is equal to GM. I can leave it in. Leave it. 1 plus, let's leave the 1 in there. I won't take the 1 out. 1 plus R0 over R0 plus RD plus RS times RS. Multiply that out, and what do I get? I get R0 plus RD plus RS plus R0. Missing a GM here somewhere. There's a GM here. Yeah. Plus R0 times GMRS. So this is equal to R0 times 1 plus GMRS. Read that. Zoom in a little bit. Yeah, sorry. You guys can read this. Plus RD plus RS. Okay? So it's R0 times 1 plus GMRS, just like before, plus RD plus RS. And why we had the RD in there, because remember, we're looking into output resistance here. So that's in series with RD. So the output resistance looking into here is going to be, you know, RS plus R0 times 1 plus GMRS, which is the good old value we had prime. If we call this looking into here as RO prime. Okay? So sure enough, it works out. So the output resistance, the large output resistance associated with this kind of circuit, associated with the negative feedback associated with RS. It's in the notes too, so if you want, I just deleted the notes. I'll do a few more examples next time, and then we'll start stability. Sure. Have it all.